I don't know. Don't forget what I'm saying. Okay. Welcome. How are you? Good. So you know how it works. So please ask me questions. So I'm trying to push myself to be as low as I can in uploading videos. I mean, I would be strongly tempted to put I was strongly tempted to put another lectures, but I hold myself because I want to see. I mean, it's better to start at a low pace, and then if to be on the safe side, and then if you are comfortable, we can sort of speed up.
So we had some problem.
Okay.
First was with the printing, and it's not able to print. I had to write all the notes again.
Yes, but that's fine, I think, right?
And
so I mean, the point is, yeah. So regarding the printing, I mean, the point is that it's not easy to. I mean, I could spend a lot of time to cut things and paste. The point is that I think it's better if I use the time to improve the overall quality of the lectures rather than copying and paste. I mean, and in general, I think you are gonna rewrite what I say anyway. So, I mean, if it is like a major issue, I can reconsider. But let's say my prior is that this is not a major issue. But if you think it's a major issue, I can change my posterior and accordingly and act in a different way. But the point is, I mean, the notes, the sort of board I send you are not supposed to be a book. It's just supposed to be a reference, right? So, I mean, for sure could be like more readable and could be written in all the best way possible. But I think, I mean, my feeling is that they're good enough. If they're not good enough, let me know again. I mean, push me to do.
No, I think that materials are really okay.
But what I'm saying is that it's, I mean, I think it's normal and it's okay that you have to copy them. I mean, that you have to rewrite what I say, because it's a way also to learn and to sort of study it. I mean, you have to redo the calculations, right? It's not just that you watch them and yeah. So.
But it takes a lot of time.
I know, but the point is that the point is that it takes. I mean, what it should take a lot of time is to understand, right? Then I mean, the rewriting is a way to checking whether you understand, right? It's not just that you read. Let's say that I'm doing a calculation. It's not just by reading the calculation that you understand if you understood, right? You have to try to redo all the steps. Redoing all the steps, it means you write, right? So you should write anyway. I mean, the fact that it takes a lot of time, it's normal. I mean, it's I think it's normal. It's part of the game in the sense that it's new material. You have to study it, and it's non-trivial. I mean, the issue is when there are distractions, right? If you have to spend a lot of time to understand what I'm saying because you don't really understand my voice, that's an issue. But if you don't understand what I'm saying because what I'm saying is hard, that's normal in the sense. Not normal in the sense that who cares? It's part of the game. Right? It's
I was thinking that if we had something like what does Professor Marsili, it's
no, yeah, I mean,
less
yes.
time consuming for us. For example, he uploads his.
No, I mean, I could write the notes on LaTeX. I mean, that's a possibility. Again, I think I prefer to sort of focus more on. I mean, in the sense that it takes time that I think it's better to invest in a different way.
Write a lot of our notes inside the notes.
No, I know, I understand.
It's less time consuming.
Yeah, I understand. I mean, one thing that it's a good. I mean, you could do. I mean, there is another point. Okay, let me skip the point because it's philosophical. But I mean, a thing that you can do, and it's actually a good exercise, is that you collectively write the notes. That is also a possibility, right? What you can do is that you, I mean, you use LaTeX, right? You create a document on overleaf, it's called, which is a collaborative thing, and you work together on the notes. right? I mean, that's also a good exercise for you in the sense that you sort of, have to study what's there and rewrite. The philosophical thing that I wanted to say is that I have considered writing the notes on LaTeX, and I decided not to also last year, because I'm afraid that it gives, it's, let's say, it becomes the reference textbook, my notes, and I don't want that to happen. The point is that I write something, I point you to references in the books, so you know where to search, and it's also good that you spend time trying to map what I say with what is written in books. I think it's a good exercise for you. It takes time, but I think that trying to understand something, it's unavoidably takes time.
Our main problem here is having not enough time.
I know. That's. When I say I know, I don't want to be dismissive of that. The program is an intensive program. Intensive means that you have the feeling. That often you don't have time. It's intensive. You have shortness of breath in the sense that you have a lot of information coming in, and you have to. It's like this. It's hard. I think you should pace yourself. We are just at the beginning, so we have a whole marathon in front of us. So, it's not gonna be. We are all together in doing this journey. So, I think it's perfectly okay and important that you raise this issue. I appreciate that you explicitly say how you think I could improve the course. But I know, it takes time, but the reason why it takes time is not because I don't write the notes in LaTeX. The reason why it takes time is because it's new material and it's hard, and understanding new things. Everybody's brain works at limited, we don't have infinite efficiency and infinite capacity, right? And so it takes time to absorb concepts. And I think that, it's part of the game, let's say. So we understand that is hard from your side. It takes a lot of time, and you don't have much time. But again, I think we are on this together.
Okay. And another problem is that the volume of sounds are very...
It's low. I'll try to speak louder. That's I tried a different. I tried to change the microphone and the speaker, but probably didn't. I tried to probably the only thing I have to do is to yell more at my screen. I'll try to do it if it is that.
It happens to me a lot that I cannot catch a word.
Okay.
And I have to repeat it for times and times.
Okay. I'll try to do that. And there was also the problem of captions. The problem of captions, it's not my fault. It's Google, how Google decides the language I'm speaking. So sometimes decide I'm speaking English, sometimes decide that I'm speaking Italian. I don't know, it's because I swear before I start the videos or after I finish it, but it's, so yes. But again, one point which I think it's very important and has not been used so far that much is use luck a lot to ask questions. Right? This Q&A here, it's meant to discuss sort of major issues, major questions, things that you don't understand, which are about the motivations, sort of the global structure of lectures or global content of lectures. If you have a question about, why there is a plus, there should be a minus, use luck, right? Because 99.9% there are going to be typos. There have been, and there are going to be typos in what I say and what I write. And this is normal when you give lectures, right? So I think that if you catch something or there is something you have doubt about, use luck. We have a channel per lecture. Post it the question you have. If it is something that you think can be solved with a yes or no, a short explanation, something that fits well on Slack, okay? Because this is also useful for everybody. Okay, I spoke too much already.
I'm searching for a question.
Yeah.
I have a question. Is it okay to ask from the bifurcation lectures?
Yeah, it's fine to ask, yes.
Okay, because I see that every time you write the differential equation, you end up with a normal form. And I just don't get very well how you get the normal form for the calculations.
Well, I mean, I actually didn't explain sort of in details how to get that, so it's normal that you didn't get it because I didn't explain. Okay, but I'll sort of try to give you, I tried to give in the lectures the motive, I mean, what is the logic. I'll try to explain that once more and to sort of clarify. So the point is that you start from, let's say, some x dot. Okay, so you have a differential equation, variable x, and the parameters q. Okay, an example. Let's write it this way. Okay, this is an example. Okay, an equation. If you want, let's write this q. Okay. Now the question we are interested in is to expand this equation close to the fixed point and close to the bifurcation point. Okay? So what is a bifurcation point? A bifurcation point is a point where actually f prime q, if you want the limit for q to c, is equal to 0. Okay?
It means the bifurcation points are the maximum and minimums, or generally extremes of functions.
Which function?
Every function.
Well, the point is the bifurcation. I mean, when we define bifurcation points, we are discussing about changing parameters. Okay, and the parameters of the equations. In this case, q. In that case, q. The bifurcation points are the points where a fixed point lose stability.
Yeah,
okay?
I see.
And so we change the stability property of the fixed points.
I mean, in a mathematics, we can describe it as the extremes of functions.
Which function?
Which function we draw here? It's general function. For example, this function. If we consider here the extremes, the maximum and minimum, those are bifurcation points.
No. The point is, so another way to visualize it is to visualize using the potential. So we can also write this as minus dv x q. Well, let's use the partial derivative since I have also dependence on the parameters. Okay, I can use that. And let's say that I have a fixed point here. Right, this fixed point is stable. Okay, because it's a minimum. And as I change q, I could, for instance, make this less stable, and then this point becomes unstable, right? So I'm just tracking the position of the point. But here the fixed point is stable, okay? And here it's unstable, and there is a point where this is like marginally stable. So if you approach from one side, you go through that, and you approach from the other side, you don't go through that, okay? And so this point here, it's a point which is the bifurcation point, okay? Is the point where you lose stability of this, right? And in fact, if you look at the derivative of this function, this is equal to f prime of x cubed is equal to minus d squared d over dx squared. So it's the concavity of the function, right? Yeah. So and you see that as you here it's positive, here it's so it's positive, so it's a minimum, so it's a stable fixed point. Here it's negative, it's a maximum, it's an unstable fixed point. Here it's 0, so that's the bifurcation point. So this is the mathematical definition of the bifurcation point. Right? So my bifurcation point QC is a point where a fixed point loses its stability. Okay? So I should write this X star first. Okay? Now, what we did is to study the dynamics close to the bifurcation point and close to the fixed point. So that means that I have a fixed point, which is the solution of f x star q equal to 0. This is the definition of the fixed point, right? And since this is a function of q, this x star is also a function of q. Okay? So this is the definition of a fixed point. Okay? And then I have like a special point which is QC, which is the bifurcation point. So I know that, let me rewrite that. If you want d dx d dx f of x q evaluated in x star q. Okay? So I take the limit of this function for q to qc, this is equal to 0. Okay? Now, what I do, what one can do to study the normal form is to expand around QC and around X star of Q. Okay? So as you expand that equation, what you can say is to say, well, let me define dx equal to x dot minus x star Q. Okay? And delta Q as Q minus QC. Okay. And what you do is sorry, here it's x. What you do is that well, this is a constant, so you can write the equation for delta x dot, and this will be equal to what? Will be equal to, I can expand, right? It will be equal to f x star qc, because I'm expanding close to this point, plus delta x df dx x star q plus dq df dq x star qc plus delta x squared 1/2 df dx squared x star qc plus delta q squared 1/2 d squared dq squared q x star c plus dq dx df dx dq plus delta x cube 1/3 delta q f dx cube plus etc, etc, and they go on and on. Okay, so I can write all the terms in this expansion, right? I'm just expanding the function f around the point x equal to x star q and q equal to qc. Is this clear? Yes. Okay. Now, the point is, in general, I have an expansion, so I can truncate in some term. Okay. Before truncating, let's discuss which term are going to be 0 for sure. Okay. Well, this term is going to be 0 for sure, right? Because this term here is 0 because of the definition of a fixed point. So this is always 0. Okay? There is another term which is always 0, which is this one here. Right? Because this is the definition of a bifurcation point. Okay? So these two terms are 0. Then all the other terms, who knows? It depends on the particular equation. Okay? So, for instance, one case is the scenario, okay, where as we approach to the bifurcation point, let me think if I want to say something else before. Well, there are okay. So So there are different scenarios, let's say. One scenario is the scenario where delta x, as I approach the fixed point, okay, the delta x squared is of the order of delta q. Okay? So the
is it an additional assumption?
it's an additional assumption, yes. It's an additional assumption. If this assumption holds, then the two leading terms are these two, right? Because these are subleading, and therefore the normal form is something like r plus or minus x squared. Okay? Okay? This is one possibility. Another possibility is that actually
is it because you truncate?
yes, it's because you truncate the other one. Yes, because if you have this assumption here, this is subleading, this is subleading, this is subleading, all the other is subleading. Okay. Another possibility is that this term here is equal to 0. Okay. So let me see. Okay. Another possibility is that this term is here is equal to 0. Okay. This actually happens when this actually happens when the fixed point is defined for all the values of q's. So if you can define x star q for all the possible values of q, which is what we can always do, you can show that this term is equal to 0. Okay. And so if this term is equal to 0, so let me say df dq in q equal to qc is equal to 0, then the leading term are these three terms. Okay? And so you have something which is, let's say, ax squared plus b r squared plus c rx. Okay? But now I can, well, I can define this as, you can sort of rewrite this term as something like r plus x squared times some constant d plus e r r squared, okay, for appropriate constant here, and I can redefine the variable x because this is an equation. Okay, I can redefine the variable x to as r. I can let's say I can define y as r plus x, and I get something which is y dot equal to d y squared plus e. Oh, sorry. No, I didn't want to do that. I wanted to do. Oh shit! I wanted to do the other way around. I think you can do these. Okay. You can always rewrite in this way. Sorry. Okay.
When you complete the
Hmm? Yeah. Just for appropriate values of the parameters. And then what you get is something like d y squared plus e y r. Okay. And this is the normal form of the transcritical bifurcation. So you make another assumption, and then you truncate the terms that are, you remove the terms that are 0, you take only the leading terms, and you get the corresponding one. Okay? Or what you can do is the third thing you can do is to say, well, there is a symmetry, right? There is a symmetry, and therefore all the like in that case, this term is equal to 0, and which this term I think was equal to 0, and you have to keep the third order term, right? And there was another one which was equal to 0, which I believe is this one. Okay, you have to keep the third order term, and what you get is a pitchfork bifurcation. Okay. So the point, I mean, I didn't want explicitly to go into these details because they are not the sort of very informative. What is informative, what I wanted you to remember is the following. When you have a bifurcation, what you can do is to expand close to the fixed point and expand close to the bifurcation point. And as you expand, you have a bunch of terms, right? Depending on the equations you started from, some terms will be leading terms and other terms will be subleading. You remove the subleading terms and you're going to end up in one of these cases, okay? You're going to end up in one of these cases, and when you end up in these, you have a fold bifurcation. When you end up in these, you have a transcritical bifurcation. When you end up in the one that I didn't write, you have a pitchfork bifurcation, right? So this should give you a sense of why you have a discrete class of bifurcations, right? Why don't I have, I mean, infinite bifurcation that are different and are defined for every different system you can imagine? Well, because you are expanding around the bifurcation point and around the fixed point, okay? I hope that this message is clear. You can sort of visualize these different bifurcation points looking at the potential as well. So how the potential change as you change the parameters, right? You can sort of do that exercise as well. Okay, so if you have I mean, for instance, the fold bifurcation, you start from something like this, and so this is V over X, and you lose stability in this way, right? So here you have a minimum, and then as you change the parameters, as you change Q, you lose this minimum, okay? The transcritical bifurcation, it's, let's see if I can do it. It's something, again you start by this, you have a fixed point which is stable and a fixed point which is unstable, okay? And then what happens is that you have something like this. What do you have? You have x squared plus yes. You basically, what you do is that you at the end you end up in something like this, okay? Which is what happens for the other so you basically you flip the stability of the fixed point, okay? And in between you have what do you have? So let's look at it. So the normal form of the transcritical bifurcation is Rx minus x squared, right? So the potential is Rx squared minus x cubed over 3. Okay? Right?
It's 1/2, I guess.
Yes, yes, thanks. So for so if R is negative, what do you have? You have that it's like this for negative R, right? Correct? I mean, you can rewrite this as, yeah. And then for positive R, what you have, yes. For positive R, what you have is again these. Why am I so confused? There is something that is it correct the normal form that I wrote here, right? For the transcritical bifurcation.
Rx minus xq.
Yes.
That is for the blue sky. I know. That's very good.
Ah, right, it's because, okay. I see. Okay, so you, yes, okay, I was confused by stupid. So I have to mark where the point is, right? So this is 0, okay? And the for positive R, this is the unstable fixed point, okay? Then I have sorry guys. So this is positive R, so this is negative R, and this is 0, okay? And this is minus R, okay? This is for negative R, this is the position of the minimum, is in negative R, okay?
Yes.
Correct. And when R is equal to 0, it's something like this, right? And this is 0, right? Okay. So this is the transcritical bifurcation, the shape of the potential. So as you move from positive R to negative R, what happens is that you change the position of this, if you follow, you have always a fixed point in 0. Sorry, yes, you have always a fixed point in 0, which changes stability properties through the bifurcation. And you have a fixed point in R, which is unstable for positive R. Oh shit, there is, that's why, sorry, the potential is defined with a minus in front.
Yeah.
That's why I was like, nothing makes sense. Okay, sorry. Okay, now I got it. Okay, so this is like V, and it's something like this. So this is 0, this is R, and this is positive R, so you have a, okay, and then you have something like this, for R equal to 0, and then you have something like this, where this is 0, where,
Yes.
yes, no, again like this, you see, it's this is 0, and this is minus R, okay? So you see how the potential change through the bifurcation point, okay? So this is negative R, this is positive R, transcritical. Okay? So you have here a fixed point in 0, which is stable, a fixed point in minus R, which is unstable. As you change this parameter, this becomes an inflection point, and you have the other stability. 0 becomes unstable, and R becomes stable. Okay? So you change the stability. Okay? So if we look at the fold bifurcation, we already discussed what it was. So if we write it as R minus this term here, right? So you have yes. So you have for positive R, you have the let's not make the mistake as before. So here I have minus Rx plus 6 cube over 3, right? So you have something like this, okay, which is R, okay, and this is minus square root of R. Correct? So this is a stable fixed point, this is an unstable fixed point, right? And that's the only two fixed points that I have. And then for R equal to 0, this becomes like this, okay? And for negative R, this becomes just something like this, okay? So you see that I go from, I mean, here you start very similarly. I mean, it looks like the same picture, just shift through the origin. As you move here, this is like sort of the same, seems similar, but then you completely change what happens next, okay? Here then you just have the same fixed point, but they are switched. Here you don't have any fixed point for finite values. Okay? So this is again the potential. Right?
I guess we can visualize it better in a platform like Desmos, where we put parameters for A and B and we change them, so we saw that how the function is changing. So
you think you prefer like this is the potential, right?
Yes.
You can plot the potential, or you can plot the derivative of the potential, which is the function, right? You can plot x dot versus x, right? I mean, it's yes, the potential it's more natural in some sense.
More visualized.
Yes, but yes. So just to conclude, so we get the last one. If you look at the pitchfork bifurcation, so you start, I mean, depends how you find the parameter, but you start like this, and then at the bifurcation point you are like, again like this, and then above you have something like this, okay? Right, so you go from 1 to 3 fixed points, 1 stable, 2 stable, 1 unstable, okay? Now, but the point I wanted to make is you can sort of understand what the normal form means in this context, right? What the normal form means is that I can expand around the fixed point and around the bifurcation point, right? And when I do that, well, this curve is are gonna always be like curves that are gonna be polynomials with the first orders in R and X, okay? So for instance, this will always be a fourth square polynomial, right? Now the point is that in reality, when you have a bifurcation with a given equation, well, these are gonna have a complicated form, whatever it is, but then if you expand close to the bifurcation, the first terms that are gonna pop up are the terms that are like the first term in the powers of x. So in this case, this potential is gonna be something which is gonna be minus r squared plus yes, x cubed over 4. Okay? Something like this, for instance. Right? If you are close to the bifurcation point. If you move away, of course, you're going to have complicated dependencies. This is the sort of bottom line, which I hope is clear. Right?
So how can we explicitly describe R?
R is just, well, it's a combination of parameters. Right? I mean,
So
if you have one parameter, it's just that parameter.
Yeah.
If you have multiple parameters, like we saw in the example of the worms, then it depends how you move in this parameter space.
So it's some kind of a variable that describes how you change a set of parameters?
Yeah, I mean, let's say that you have only one parameter,
Yeah.
then it's just
That parameter.
that parameters, like sort of, let's say, in this case, rescaled such that it's 0 at the bifurcation point.
Okay.
Okay? So if you have a parameter q, for instance, r could be like, let's say, q minus qc times some constant. Okay? Doesn't matter, right? You see, it doesn't matter whether this is minus 3 or minus 37, right? For the bifurcation point of view. Yes?
I'm very lost.
Sorry? Yeah.
I'm very lost. Why you expand? You are looking for the Lyapunov parameter, because I check my course, I noticed that the expand to find the Lyapunov parameter, but here I don't know what we are looking for exactly.
Why you are talking about the Lyapunov parameter?
Since you use the
V.
you expand, you
Mhm.
expand, because I noticed that you expand something, and when I check my course, I noticed that they use this form to find the Lyapunov or to solve the differential equation. I don't
Well,
know
What's the goal of this
difference.
expansion?
Yes.
The goal of this expansion is to show you, I mean, what I wanted you to learn is that there are few classes of bifurcations. This is my point. My point is that when you have a bifurcation point, what is a bifurcation point? A bifurcation point is a point where a fixed point loses stability. Okay? Now, in principle, you can imagine that it can lose stability in billions of different ways. What I wanted to show you is that there is a discrete, fairly small set of way to lose stability. Okay? So it's possible to, if you want to say to be slightly more formal, it's possible to classify bifurcation points in a few discrete set of types. Okay? That's what I wanted to show you. Okay, so you have a bifurcation point. Before these lectures, you could say, oh, I mean, everything could happen. Here, well, you can sort of classify this bifurcation in fold bifurcation, transcritical bifurcation, or pitchfork bifurcation. Okay? How can you do that? Why can you do that? The reason you can do that is because you can expand close to the bifurcation point, close to the fixed point, and only a small number of terms are going to survive, depending on the type of bifurcation, and the terms that are going to survive are the ones that determine the type of bifurcation. This is what I wanted to show you. Okay?
This concept of the bifurcation point, where a fixed point loses its stability. So, it can be otherwise. I mean, unstable point.
Yes.
Stable.
Yes.
Okay. So, is it like a mathematical concept or ecology, or it's a concept in ecology?
The bifurcation point?
Yes.
No, it's a mathematical concept, right?
So,
but one thing that I sort of put under the carpet is that in some scenario like this, here you have a fixed point, here you have a stable fixed point, here you don't have a stable fixed point, right? So if you are here, what does it mean to expand close to the stable fixed point? Nothing, right? here it means something. So when you take the limit of Q going to QC, you have to take it from the right side. Okay? So for instance, here you have to take the limit as you are for R positive, and you take the limit up to 0 with R going to 0 plus. Okay? In terms of this function, it doesn't change. I mean, this is just a small complications in terms of small conceptual complications, but it doesn't change anything about the calculations. Right? But the point I wanted to make is I'm not sure I understand I mean, the point here is that in some cases you have a fixed point on both sides of the bifurcation, in others you don't. Right? So for instance here, actually the transcritical bifurcation is the only case where you have a fixed point. You have two fixed points and they exchange their stability in some sense. In the other case, you sort of, here for instance, you have fixed points and they disappear, right? In that case, you have a fixed point and then you split them in two. But the point is that on one side of bifurcation, you always have a stable fixed point. That's the whole point.
I want to know what are for the real application of this buffer point for in ecology.
Well, I mean, the point is okay.
So, as an example, so can we, for instance, say so this population have this parameter, and if we change this parameter in this population, we're gonna have this outcome.
Well, yes, in the sense that I mean, and the specific example is the lecture number 4. The one on the wall, right?
Yes.
In that case, we have parameters, the growth rate and the carrying capacity, rescaled in some way. And as you change them, you have different different phases. So these are separated by bifurcation points, right? Yeah. And then you can, I mean, for instance, one thing that it's surprising is that you slightly change one parameter, and you can jump in the fixed point of a large amount, right? Or vice versa, you slightly decrease the growth rate and then have a collapse, right? The point is, all these, I mean, what is interesting about bifurcations is that, well, you could think that all the equations here are one-dimensional, everything is smooth. If you think about all the trajectories are smooth in time, they are analytic function of times. Everything is very well behaved. Nevertheless, we have interesting abrupt behavior if we look at the fixed point, the stable fixed point, as a function of the parameters. Right? This is what is surprising and interesting. Right? And in some sense, it's the only surprising things that you can have in one-dimensional systems. Right? That fixed points change their stability, and change their stability sometimes in a surprising way. So, for instance, in the worm example, we have that, let's say, let me do this. We have rho and k, right? The two rescaled parameters, and we have these phase space, and we have three phases, right? 1, 2, and 3. Okay? And let's say that we move in this direction, in this line. Okay? What happens? Well, actually, let's say that we move on this line first. We move on this line first. And for instance, how do we move on this line? For instance, let's say that we are here, and we are the people that manage the forest, and they want to kill these worms. Okay? So we spray pesticides. Okay? That is something that decreases the growth rate of the population. Right? So we are here, and then we try to move there. Okay? Then, if you look at the fixed point, if you want n star, okay, I can put n star, as a function of the parameter here rho, on this line here. Okay? So as we, let's say that, yes, let's say rho. So So what we have is that we start from a high value and we decrease from a low value continuously, happily, without any sort of sudden change, right? If we increase the amount of pesticides, the population is going to decrease of a fair amount, right? On the other hand, here the situation is much more complicated, right? Here the situation, if we start from I row, we are here and here, right? Right. So, for instance, let's say there was, I don't know all the physiology of this, but let's say that they grow in the summer when it's warm, right? Let's say in the winter we were here, right? Then temperature changed, they grew here, and then they are here, right? And then we realize, oh shit, there are all these worms around. Let's kill them with pesticides, right? And then you have to go back here, right? Yes, I mean, and up to this point, you're going to have a population which is like, yes, I mean, smaller than this, but still big, right? Then you increase of 0.01%, and then you jump down here, right? So this is cool, I think, in the sense that you have like a big change, a big effect, changing a small value of parameters, right? And this can be positive or negative, right? You can say, well, this could very well describe like an example of fishing, right? You fish, and if you increase too much your fishing pressure, then you arrive at a point of collapse when you kill everything, right? And then, I mean, to restore the population, it's not just that you go back and you fish one less fish a day, right? You have to really go back, right? Okay? And you can think that as, one of what people believe is that, well, we are somehow here, okay? And this is increasing temperature, right? So perhaps, this being like the global population of insects, for instance, or the fishes in the oceans, right? So we are here, or the state of the ecosystem at the global level, right? We are here, and we are moving here as the temperature increases, and we are close to a point of collapse, right? So perhaps, you say, well, the temperature is going to increase by 0.5 degrees in the next, 10 years, and you say, well, 0.5 degrees, come on, I just opened the window, it's 1 degree, whatever is going to change, right? But that is the small change that is enough to have the collapse. And then once you're here, you're fucked up, right? Because then it's going to take, right? A lot to go back, right? So this is the motivation, this is why it's interesting, right? So again, note that saying this is a different thing to say, oh, this value here corresponds to an average temperature of the ocean of 24.50567 up to the decimal digit of temperature, right? So saying this as what could happen is different from knowing what are the parameters of this critical point. But this shows you that this interesting, surprising behavior can emerge in a setting which is fairly simple, which doesn't require sort of very complicated functional form with weird dependencies. Right? Yes.
My question for that part, from the from the population equation. From the equation for the population.
Okay.
You added a predation term.
Yes.
Subtract.
Yes.
And then, how do you know that this is the right form?
Okay. So I know that because someone did an experiment, not me.
Okay.
But let's say someone did an experiment, and so I know that in absence of predation it would be something like this. Let's say, I know this is a reasonable choice, right? What does it mean, a reasonable choice? Which I expect that it's going to be something that is positive, and it's going to be something that becomes negative as a critical value of k. So this is like a reasonable choice. And then I say I have a predation term, right? And this is some p of n, okay? So how do I know what is the form? Well, what I can do is that I can take a tree I can, for instance, count how many worms there are on this tree, and then watch it for hours and say how many birds eat these worms. And what I can do is I can plot basically how many worms are killed as a function of the worms in the tree. Okay? And I see a curve which is, it saturates, and it does something like this. Okay? So, what is the shape of this curve? Can be many different things. Let's say that I want to do something simple. It's going to be something like n squared 1 plus n squared. Okay? Let's say b. Okay? Well, then you can say, but what happens if I choose a different form? If instead of this form I choose the error function of the cosine, of the hyperbolic cosine of the square root of n, right? Well, you could say, how much do you think is going to change? A lot? I don't know, or probably a little?
Probably a little.
Why?
Because the functions have the same shape.
Yes, and if you think about how did we find this plot here?
We use expansions maybe.
Yeah, we use expansion here, but we also use graphical methods, right?
Yes,
So we basically, to find the exact shape of, exact position of this point, we actually use that specific function. But overall, what we did is to plot, let's say, p of n over n, and say it's something like this, right?
So we mainly care about the behavior of the function.
Yes, that's the point. The point is, I know that it's, on one hand, you see, well, this is over-parameterized, you have many parameters, you have to make many choices, and it's true, right? The point is, this property here, it's quite, it's very robust on the choices I made, okay? So you can play with other choice, and you are going to find very similar behavior, right? Because at the end, the only thing that mattered was that this was growing and then was decreasing, right? This p of n over n, which is the function we plotted to, okay? When we use the graphical method to find the solutions. Okay? So that's the main thing, right? Now, of course, then you can have very complicated forms which actually here intersect more than once, etc. It's possible that you have more complicated behavior, right? But overall, you expect if you have something that has a single inflection point, it's going to be something like that. Okay? So it's fairly robust to the functional form. It's fairly robust to the parameters in the sense that, this is a function of the parameters alone, and of course it depends where you are, but this is the behavior you're going to have. Okay? Yes?
What is the meaning of the intersection point?
Yes, I didn't write it well, but okay, let's do the steps. So we go there. So the first thing we did was to rescale. We rescale the parameters. Okay? We rescale the parameters. We defined tau equal to AT and n equal to u equal to n over b. Okay? And then we got an equation that was u dot rho u1 minus u minus u squared 1 plus u squared. Okay? So let me call this function, how do you want it to call it? Q of u. Okay? So what are the point where, I want to find the fixed points. The fixed points are obtained when this function here is equal to 0, right? So the points where this function is equal to that function are the fixed points, okay? So I plot this function here. Well, I don't need to have a name. So this function is u, okay, sorry. So then everything is at least proportional to u, so I can write this as u, which multiplies rho 1 minus u minus u over 1 plus u squared, okay? Correct? Okay. So I have one fixed point, so I want this left-hand side to be equal to 0, choice A, u is equal to 0, you can check u is unstable, u equal to 0 is unstable, right? We proved that. So then, if I want a solution which is not the worms are extinct, so u is equal to 0, I have to put this equation here equal to 0. Okay? This is equal to 0 if this term is equal to this term. Oh, here this is okay. Okay? So I want this equation here to be equal to that. So let me plot this function here. It's something like this. Okay? So what is the function there? Well, it's something that in u equal to k is equal to 0, and in u equal to 0 is equal to rho. Okay? So it's something where this point here is k, and this point here is rho. Okay? And these are the two parameters. Okay? So for instance, if I increase, here I have just one point, so here I have one fixed point. Okay? If I increase k, here I have another fixed point here. Right? So the fixed point went up. Right? Because, yes, u increased. Okay? I can change it a little bit more, and when I end up is I have three fixed points, these, and that. Okay? So the point where this curve intercepts the others define the fixed points. That is, yeah. Go ahead. You have, did it click? Okay.
No, this is related to my question.
Okay.
Yeah. So for you got that expression from the experiment.
Uh-huh.
Yeah. But you knew that there is hysteresis in the population because of this patient.
Well, I don't understand if that is an ontological or epistemological question. So, is that about what you knew before doing the experiment, or what you wanted to prove, or you can say, let's put it this way. So you have these worms, right? You know two things: they grow and they eat trees. If there are not trees with green leaves, they are not going to grow. So that is the logistic part. Okay? And then the other thing you know is that birds like worms because they are like candies to them. Okay, so if they find a worm, they're going to eat them. Now the question is, well, how is predation depend? So how many worms are eaten by birds as a function of how many worms you have? Okay? Clear? This is the P of n. Okay? This could have very different forms, right? You could say, well, it's the simplest thing ever, right? You could say P of n is just equal to n times a constant a. Okay? If you double the number of worms, then you're going to have twice as many worms eaten by birds. Okay? So this P of n is how many worms per unit time are eaten by birds. Okay? Parenthesis. We are assuming that the bird population is constant, so it doesn't change in response to changes of the worms. If they don't have worms, they're going to eat something else, but they like very much the worms. It's like very juicy food for them, right? So if this is linear in n, you can say, well, simply there are more worms, there are going to be more that are going to be eaten, right? This is one possibility. But also you can say, well, let's say that I have infinite worms. Do I have infinite predation? Well, no, because a bird, after a while, it's like its stomach is full, it doesn't think to want more, right? So you expect that if you have too many, it doesn't change how many are eaten, right? So it's like if you have one slice of cake, you're probably going to eat it. If you have two, well, you're probably going to eat it, right? If you have 300 cakes, well, you're not going to eat 300 cakes, right? Sorry for the but this is like what happens.
Just the simple example of how COVID spread. So the idea is there is point where COVID will stop because everyone is going to be infected.
Yes, it's different.
No,
we're going to discuss that explicitly in one of the next few lectures. But it's different that.
No, I'm just talking about the point where
Yes.
things are enough, and when it is enough, there is.
Well, I mean, perhaps, yeah, in a sense, it's the same thing. Okay, yeah, I mean, okay, in some broad sense, it's the same thing. I mean, it's really that if you are a predator, so you need time, and I mean, you need time to eat, and then you are full for a while, right?
Yeah.
So there is also a rate at which you are full. So I didn't want to open. I mean, we are going to see that more explicitly when you're going to also model the dynamics of predators, but let's forget it for a while. So you can think at something like this, right? Or another form. You can either make different assumptions, which is a possibility. So you can say, oh, if I have something like this, what is going to be the dynamics? If I just add a term like this, okay? Or I can make different choice. Or someone did an experiment and told you what is the shape of this function, okay? What experiment do you do? I mean, one possibility that you can do is you choose a tree, you count how many worms you have, and you look in a day how many worms are eaten, okay? And then you repeat for a different tree with a different number of worms, okay? And you look at how many are eaten as a function of the number of worms you had at the beginning, and that is a proxy of this P of n. Okay? So if it is linear, if that number is linear, then probably it means that this is linear. If that saturates, it means that this saturates. I mean, it's a proxy of this shape, right? And so your experimental friend did an experiment and measured these numbers here and found something like this. Okay? Collected 9 data points, I mean, something, and you say, well, let me fit a line to that. It seems that is something that grows and then does something like this. Okay? Then you come, you do the model, and you obtain this. This is like the. Was this the question you asked, or not? It's fine if it is not. It's just I want to be sure.
Because when I read the paper, I think we still have to argue that this is, for example, for Budworm, we still have to argue that the predation dynamics of their system is equivalent to the experiment.
Yes. No. Yes. I mean, this is. I think that this is the assumption I said earlier. That you are assuming that the population of birds, for instance, is unaffected by the amount of worms, right? And of course, I mean, you are assuming that your experiment is a proxy of what happens at the population scale, which, I mean, it's a big assumption. I mean, you could say, well, perhaps I'm looking at what happens in this tree, but that's not representative of the whole populations. Yes, all these things are possible. But, again, the idea is measuring how much these birds are going to eat worms on a given tree. It's a proxy of what is the, right? It's a proxy. It doesn't mean that that is correct. Okay.
Another question. So if we're gonna model a system with predation, we use the equation and then it will be already accepted.
Well, accepted in what sense?
In a sense that accepted in a sense that it's valid.
Well, I mean, the one important point is when you're trying to model a natural phenomenon, you always make approximations, right? And these approximations, you agree or? Okay, well, because like you said, okay. No, yeah, I mean, it's fine if you disagree, it's interesting, but you always make assumptions, right? So whether these assumptions are valid or not is somehow based on what are the predictions you make with the model that you formulated with those assumptions, right? So is it okay here to assume that the population of birds is fixed? I don't know. I mean, it depends, right? How it depends? Well, one thing you can do is that you can, I mean, here you can make predictions, right? You can say things like, oh, if I double the amount of pesticide that I put on the system, I'm going to obtain this amount of change in the population. something like this, right? And these are all prediction, and you can test this prediction. If data are not valid, then it means that you neglected something perhaps important. Or if you want even more on the topic, you can say, well, I could design an experiment where I also do birds surveys. So I also look what is the population of birds. And I can see whether the population of birds is somehow correlated with the amount of worms you had in the past years, for instance, right? And so you say, well, if it is not correlated, it's constant or fluctuates somehow a little bit, then perhaps this assumption is correct, because I'm saying that basically how many predators there are, it somehow doesn't affect the predation pressure, right? If that changes, I should say, well, perhaps this term depends also on how many predators I have. We're going to see that explicitly in a few lectures, right? And so you can do that.
So this hysteresis behavior is still open for proving?
Huh? Well, I mean, the point is, you can say, okay, so you can say how robust is this thing? Is it because I choose a particular set of assumptions? Well, I can say no. I don't know if that is enough, probably not, and it's okay that it's not. The point is, I mean, you can include details, like you can say, oh, I have the population of birds, etc., etc. Now, as you make your models more complicated, typically these models also include the previous model as a sort of particular choice of the parameters, right? So, for instance, you assume that there are birds and you want to model the population of birds, then you also will have an equation for birds, and these two equations are coupled. If you say that the population of, the dynamics of birds is much slower, let's say, then you can neglect the changes in the birds because they are going to be practically constant, right? And so in one limit of parameters, it reduces exactly to this point. So it will exist a range of parameters for which this is going to be still valid, okay? But again, you can think of, well, perhaps I've done this model, this works, and then I can try to say how my models can break, right? So I can say, what are the predictions that my models can be used to falsify these models, and you can try to falsify the model, right? And alternatively, you can try to add more details and show that some prediction of the models are robust as you increase these details, right? So these things here is fairly robust, right? Because if you see, it's not because I chose a particular shape of the function here, right? I mean, yes, it's a particular shape. It's something that goes up and down, but I didn't really use the fact that it was this function or something that has the same shape, right? So if I had, let's say, something like u, now this function here is u1 plus u squared, okay? Probably if I had something like u1 plus e to the u, I would have had the same, exactly the same properties, right? Quite reasonably, okay? Because it's something that for small u, well, this is like subleading in this, or actually I can do something like this, okay? For small u, this is subleading, so this goes up and down, right? Yeah?
From that, how do you study the stability of those fixed points we get here in the class?
So you, well, this is still a one-dimensional system, so what you do is to look at, so you have a fixed point, I mean, you have two ways to study the stability of fixed point. I mean, you have many ways. One way is to, you take the fixed point, you have an equation here which is like some f of u, you compute df over du, you evaluate in mu star, and you check whether this is lower than 0. If that is the case, then a stable point. This is like sort of, let's say, the analytic method. then you can have a graphical method. Okay? So what you can do is that you can plot u dot versus u, okay? The points where, or if you want, f of u versus u, okay? And the points where this f of u intersect in 0 are going to be stable or unstable. I mean, are going to be the fixed points, and depending on the side in the neighborhood, those are going to be stable or unstable. For instance, you have something like this, okay? So these are these, and these are the fixed points, okay? Now, here it's u dot, so this is the derivative, and this is positive, this is negative, this is positive, so this is a stable fixed point. Okay? Right? And the other two are unstable. Okay? The point is, I mean, should I use one or the other? Okay, so if you are in more than one dimension, you don't have choice. But if you are in one dimension, should I use this or this? Right? It depends. Right? This is more immediate. It's something that you can sort of, you have just to plot a function. This is a little bit more complicated in the sense that you have to calculate explicitly the fixed point and calculate explicitly the derivative of that fixed point. Right? So it requires sometimes a little bit more calculations, right? Perhaps you have to solve here equations that you are not able to solve exactly, right? Right? Because perhaps it's I don't know, equations which involves like complicated functions, and you are not to say, oh, this value here is square root of 3 times a divided by hyperbolic cosine of b. They're not able to reach well-defined expressions. Well, with the graphical methods, you know that there is this value and it's going to cross 0 in some point. Okay? So this gives you the qualitative pictures. If you want to put numbers on these pictures, then you have to solve the equation explicitly. Yes.
About the part with the 2D linear system.
Okay. Before, just a second. Before we move to that, I mean, because it's like sort of we are stepping to another. So I want to be sure that there are no questions on this, and then we can move to the other lectures. Okay. Are there more questions on these words? Yes.
Since here you said you can plot u dot function of u. I know in some cases we have to find the fixed point for u dot equals to 0, and sometimes you get some expression which we are going to plot and yield the kind of bifurcation we have.
The kind, sorry, of
Bifurcation.
I'm not sure of what.
Okay, if you consider something like x dot equals to let's say x squared minus let me check this.
I mean, was a specific equation you had in mind, or?
Yes, is okay.
X squared minus?
It was remove it inside the bracket r1 minus 2.
Sorry?
Inside the bracket r minus 2 x plus 3 x cubed.
Okay.
Yeah. And we want to study the stability of this system.
Yes.
And you said we can plot
Yes. I mean, so the only parameter is this r, right?
Yes, r is small r.
Yeah. Let's say that r is larger than 2.
Yeah.
Okay? So if r is larger than 2, this is positive, right? And this is positive. This means that, okay, so for sure I have a fixed point in 0. So let's look at the fixed point if you want. I have x times r minus 2 plus 3x squared. Okay? So I immediately see that if r is larger than 2, there is one fixed point for
0.
0 is always a fixed point.
Yeah, it will be the only one.
Well, it depends whether this is positive or negative, right?
Yeah, but
For r larger than 2,
for
yes.
R,
Yes. For r larger than 2, it's something like this, right?
Yes.
So there is one fixed point in 0. Is this fixed point stable or unstable?
It's unstable.
It's unstable, right? Because this is x dot x. So this is an unstable fixed point, right? Then I have r equal to 2, okay? And so this is going to be something like this, okay? So this is again a fixed point. If you compute the derivative in this fixed point, it's going to be 0 in 0. The second derivative is going to be 0. The third derivative is going to be positive. And therefore this is an unstable fixed point. You can immediately see from the graph that this is an unstable fixed point. Right? Because the equation in r equal to 2 is x dot equal to x cubed over 3. No, times 3. Okay? So this is one of the cases where if you take the first derivative and you evaluate it in 0, the first derivative evaluated in the fixed point, the first derivative is equal to 0. So then you have to go to the second derivative. Okay? The second derivative in this case is 0. So you have to go to the third derivative. And the third derivative in that case is going to be positive. Right? It's going to be a constant. Right?
80.
Yes.
Yes,
3 times 2, 6, 3, yes, 18. It's going to be 18, which is a positive number. Okay? And therefore the point 0 is unstable. But you can immediately see from the graphical method, right? This is x dot, here it's positive, here it's negative, so you depart. And if you have r lower than 2, then what happens? Then you have something like this. Sorry. Something like this, okay? Where this point here is minus square root of r minus 2 minus r divided by 3. And this point here is square root of 2 minus r divided by 3. This is 0. So what is the stable fixed point? Well, this is negative, this is positive, this is positive, this is negative. So this is a stable fixed point, and these two are unstable. Okay? So this is what bifurcation is this? Subcritical or supercritical? I don't remember, I never remember which of the two, but is, I think, supercritical. It's the one where you have one fixed point which is unstable, and then you have two fixed points which are unstable, and one that becomes stable. Is the uninteresting one, in some sense. Okay? So you can do this with the graphical method without plugging this equation here. Now the interesting point about the graphical method is that in this case you can do both, right? But I could then give you a much more complicated form which have exactly the same behavior, right? Okay, so if I gave you, let's say, x dot equal to the hyperbolic sign of all of these, right? I mean, this is in some ways is cheating because I just put an odd function over there, but so it's simple. But you can, I mean, you can imagine something more complicated, and still will have the same behavior. Okay. Well, probably you could have done. Well, okay. Well. Well, no, I wanted to say you could have something like this, perhaps. Let's say x. Okay. In this case, everything should work the same way. Hopefully.
I guess even in the first one, it
Yeah.
works the same because for x point equal to 0, we have to solve what is inside the equal
Yes.
to
Yeah. Exactly.
equal
So
to zero.
yes.
So
Yes.
we-
Anyway. Yes. Okay. But the point here is, I mean, you can try to solve the equation, compute the derivatives around all the fixed points, sort of the analytic method, or you can plot the functions. They are equivalent, right? In one-dimensional case, you can do both easily, and the graphical method is in some sense more immediate. In higher dimensional systems, doing the graphical method it becomes impossible, unless you're able to plot things in 4 dimensions. Okay? Yes?
How do you deduce from this result the bifurcation diagram?
I didn't deduce the bifurcation diagram. I deduced. I mean, the bifurcation diagram is basically this, right? But I deduce what type of bifurcation is, and it's simple, right? Because you go from one fixed point, and then through the bifurcation point, you have these 2 other fixed points which lose. I mean, this is, in some sense, this is the definition of a pitch for bifurcation. As a superficial pitch for bifurcation, right? Now, actually, in this case, it's very close to the normal form. You could have much more complicated dynamics, but if you see something like this, then it's a pitch for bifurcation, right? Because it's the standard example of a pitch for bifurcation, right? For instance, if you had here a -3, that would have been a subcritical, okay? Because you would have switched all these things and R.
Last one.
Yeah.
What's the meaning of the critical point in the biological meaning?
The biological meaning is if you are changing parameters and you are close to a critical point, you can expect that your system has abrupt changes close to this critical point. Right? So the biological meaning is you change parameters, there are points. I mean, I'm not clear what you mean biological meaning of a mathematical concept, but the biological interesting aspect of this is that you change parameters, and there are points where a small change of parameters corresponds to a large change of the dynamics.
Like the stable point.
Yeah.
I mean, if we are close to the stable point and we change the parameter, we will still almost remain in the same population. Like.
Yes, I mean, imagine here. I mean, this is like not. I mean, whatever this is, this cannot be populations because they're also negative. But let's say that these are something, right, with some meaning. I don't know what is that, but you are here. You are close to 0, and if you start with this initial condition between these 2 points, you end up here, right? So the point is that if you slightly perturb this, then you are always going to end up here, right? Then you pass the bifurcation point, any small perturbation will drive you away from the system. You're going to go to negative values, right? So close to the bifurcation, I mean, above the bifurcation point, you are somewhat stable. Below the bifurcation point, you become unstable, right? You change the stability property of the fixed point.
We can compare the stability point to the current capacity.
With?
with the carrying capacity. Can you compare to the carrying capacity?
To the carrying
Carrying capacity.
well, I mean,
Since
you can, well, if you look at this example here, right, and you move on this line, okay, none of these points is the carrying capacity. Actually, the carrying capacity is like something like this, okay? It's above all these points. The point is, these points here are dominate, so this is the population of worms, right, as a function of rho, and this is U star. So all these points are dominated by the carrying capacity. So you are close to the carrying capacity, but there is some predation that push you a little bit down. Here, your population is determined by predation. So basically, you are kept low because, like, as new individuals grow, they are eaten by birds. Okay, so you have these two fixed points, these two stable fixed points, which differs in that respect. But these are not mathematically equal to the carrying capacity. Because, like, the fact that you have predation always push you a little bit lower than carrying capacity. Okay. Is there any other question on this part, or we can move? Actually, we don't have much time, but we can move to the linear system. Linear system. Any question on the linear? If you want, we can move on the linear algebra part.
About the 2D linear system.
Yes.
I didn't really understand. How you got the eigenvalues for the two?
The last. So it's the last. You mean the last part? The last things we discussed. So I just said, let's say that you have a two. Okay. So what I showed, this is like the question we have. Okay. What I showed is what is that the solution, the dynamical behavior depends only on the eigenvalue of these metrics. Okay. Now this is a real matrix. Okay. So I know that if, in general, if lambda is an eigenvalue, then the complex conjugate is an eigenvalue. Okay? This is a fact that a linear algebra fact, if you want.
Only if lambda is complex.
Well, if this is, if the imaginary part of this is 0, then this is a tautology, right? If a real eigenvalue is an eigenvalue, itself is an eigenvalue. I'm not saying there is another eigenvalue, right? I'm saying if you have an eigenvalue equal to lambda, there is an eigenvalue equal to lambda complex conjugate, right? If the eigenvalue is real, then this translates into if lambda is an eigenvalue, there is an eigenvalue equal to lambda, which is true. Okay? So this is true only if the matrix M is real, right? Okay. So given this fact, when you have two by two matrices, right, you have only a bunch of scenarios, right? So if the imaginary part of one eigenvalue is equal to 0, then necessarily the other eigenvalue has to have 0 imaginary part, right? Okay? And the reason is that if this was not true, then it means that the other eigenvalue has to be equal to the complex conjugate, and therefore that should also have a non-zero imaginary part. Right? So this is one. So it's probably better to imagine that you are plotting the eigenvalues in the complex plane. Let's say that you have like the complex plane, and you have the real part of eigenvalues and the imaginary part of eigenvalues. Right? So since the eigenvalues have to be complex conjugate, if you have something that is not on this line, you also have the one that is mirrored on this line. Okay? This is the complex conjugate. Okay? So what I'm saying is, if one eigenvalue is equal to here, is like as zero imaginary part, the other cannot have a positive or negative imaginary part. Right? It has to have an imaginary part equal to 0. Because if it was here, then that could not be there. Okay? This is one case. So if both are real, then basically, it's the same as the case where the matrix is symmetric. So if the real part, let's say the max between real lambda 1 and real lambda 2 is negative, then you have a fixed point which is stable. 0 is stable, right? So you converge to that. Then if max ready lambda 1, lambda 2, then that fixed point is unstable, right? So there is at least one direction where you move away from it. Okay? Then if the imaginary part of lambda 1 is different from 0, okay, then the imaginary part of lambda 1 has to be equal to minus the imaginary part of lambda 2. And the real part of lambda 1 has to be equal to the real part of lambda 2. Right? Because if I have a point here, the other eigenvalue is going to be here. Because it's the complex conjugate. Right? So in that case, if the real part of this eigenvalue is the same real part, so if the real part of this is lower than 0, okay, then this is a fixed point, okay? But since you have an imaginary part which is non-zero, you are gonna go to this fixed point spiraling, spiraling to that fixed point, okay? So it means that if you look at the, this is x1, yx, sorry. If you look at, for instance, x over time, what you're going to see is that this oscillation decreases in time and tend to 0.
How did you find out that?
The oscillations, the fact that there are oscillations, well, we obtain the solution, right? We obtain that the solution x of t, y of t, right, can be written as like a, well, in general, if you have a high-dimensional system, x of I can be written as the sum over the eigenvalues of some expression here where you have v alpha, L alpha, e to the lambda alpha t, okay? Now, in the 2D case, you have only two eigenvalues. If they are complex conjugate, right, you have something where you have vi1 L 1 e to the lambda 1 t plus v2I L2 e to the lambda 2 t. Okay? Now, the point is that since you have a two-dimensional system, lambda 1 and lambda 2 are complex conjugate, and also this value here are complex conjugate. So here you can write lambda 1, and here you can write lambda 1 complex conjugate, lambda 1 complex conjugate, vi complex conjugate. Okay? And so you are summing a complex value plus its complex conjugate. Okay? So this is equal to 2 times the real part of vi1 L1 e to the lambda 1t. Okay? And what is the real part? Well, it's the absolute value, okay, plus the imaginary part. Okay? Plus, sorry, you can write the real part, let me do in steps. We did it, but so you have something which is the real part of some z e to the lambda t. Okay? Well, this is a complex number. Now, I can write z as the absolute value ei theta, and I can write e lambda t as e to the real part of lambda t plus I imaginary part of lambda t. Okay? And what I get? I get that the real part of this is going to be z e to the real part lambda t times the real part of e to the I theta plus e to the imaginary part of lambda t. Okay? Right? What is this? There is alpha 2. What is this? Sorry, this was 1/2. Well, this is the cosine of theta plus the imaginary part of lambda t. Okay? So you get that the solution is something, I mean, some real number, e to the real part of lambda t plus the cosine of the imaginary part of lambda t plus some theta. Okay? Which actually depends on the initial condition. So if you plot this, what you get is, so this is like e to the minus real e to the real part of lambda t. Okay, assuming that the real part is negative, so this is stable, and this is the cosine, so this is something that does like this. So if you take the general formula that we got in an arbitrary large dimensional system to the 2D cases, you can make some simplification due to the fact that if all the eigenvalues are real, well, everything is as before. If you have one eigenvalue which is imaginary, also the other eigenvalue is imaginary, and therefore basically you have just this expression here. Okay? It's hard to infer the face from behind the mask, but I perceive some level of confusion.
I think I don't know how you got
the spiral. Oh, okay. So I have to go in like 3 minutes because I have the Zoom now. So one possibility is that you join to the Zoom, but I don't know if that is the best choice. But how did I do that? Well, the point is, okay, the point is you have x and y of t, right? Okay. So you can write an expression for both of those, okay? For both x and y. And if you do that, you are going, sort of what you have to do is to project on the eigenvectors, both of them, right? So, but what you're gonna get if you do that is the cosine of, well, here, some value which doesn't really matter. Let's say that this is a constant, doesn't matter. In general it's not, but let's say that it is. You have here the imaginary part of lambda plus t, t plus some theta 1 e to the minus the real part, e to the real part, okay? And there you have the cosine, the imaginary lambda t plus theta 2, okay? Oh. Okay? Now, these theta 1 and theta 2 are determined by initial condition, because they involve the projection of the initial condition on the eigenvector. So they depends on the initial condition. So let's say that I choose the initial condition where this is 0. Okay. Okay. If you do that, you're going to realize immediately that this is going to be pi over 2. Sorry. So what is the cosine of something pi plus pi over 2?
Sine.
It's the sine. Right? So here you get the sine. Okay. Now imagine that you don't have this term. This is like a cosine and this is a sine. So this is like something that goes on a circle. Okay? Where the amplitude is the term which is in front, which I even described. Okay? Now, what if you have this term? This term is equal for both. So this term corresponds to the fact that you have an amplitude that is changing over time. So imagine that I'm circling, and then I have this term here. What this term does is that it shrinks the amplitude as I go. Okay? So this was the 3-minute answer to your question. I hope that it gives you the right way to go to. So my suggestion is take the full expression for I-dimensional system, right, which we wrote, with all the projections, and then apply it for the 2-dimensional case. Okay? So let's stop.